What if the interstellar visitor we've been tracking isn't traveling alone? What if 3I Atlas, the mysterious object that crossed the threshold of our solar system in 2024, is merely the herald of something far more complex? Tonight we venture into territory where astronomical observation collides with cosmic uncertainty, where the comforting explanations of conventional science begin to crack, and where the implications of what might be following this wanderer from the depths of space force us to confront questions humanity has never truly prepared to answer. For months, astronomers have trained their instruments on 3I Atlas, cataloguing its trajectory, measuring its composition, calculating its origins. The official narrative is clean, scientific, reassuring. A rogue comet from another star system passing through our cosmic neighborhood on a journey that began long before human civilization emerged. Just another data point in our growing catalogue of interstellar objects. Nothing to see here, move along. But what if that narrative is incomplete? What if, trailing behind this cosmic wanderer at distances that challenge our detection capabilities, something else is making the same journey? Not a single object, but multiple objects. Not a natural formation, but a pattern. Not random debris from the stellar void, but something that bears the unmistakable signature of coordination. A swarm. The word itself conjures images that make us fundamentally uncomfortable. Swarms imply intention. They suggest collective behavior, purpose, direction. When we think of swarms on Earth, whether locusts darkening skies, bees moving as a unified organism, or schools of fish turning in perfect synchronization, we recognize intelligence of a kind, distributed decision-making, emergent complexity arising from simple rules followed by countless individuals. Now transpose that concept to the cosmic scale. Imagine not hundreds but potentially thousands of objects, each perhaps the size of a city block or smaller, maintaining formations across distances measured in astronomical units, following in the wake of 3I Atlas like a flotilla sailing behind a flagship. The implications are staggering. If such a swarm exists, if it's real and not the product of observational error or wishful pattern recognition, then we face scenarios that span the entire spectrum from natural cosmic phenomenon to something that challenges our understanding of what's possible in the universe. Are these fragments from a stellar collision gravitationally bound in ways we don't yet understand? Are they ice particles ejected from 3I Atlas itself, creating a debris field that mimics coordinated movement? Or, and this is where speculation ventures into territory that makes professional astronomers nervous, could they be something else entirely? Something that moves with purpose? Tonight, we're going to explore this possibility from every angle. We'll examine what we actually know about 3I Atlas, look at the data that's emerging from multiple observatories worldwide, and then venture into speculative territory to ask the questions that hover at the edges of mainstream scientific discourse. What would it mean if we're not alone in monitoring this interstellar visitor? What protocols exist for scenarios that fall outside standard astronomical categories? And perhaps most importantly, how would we even recognize the difference between a natural phenomenon and something designed? This isn't about promoting conspiracy theories or abandoning scientific rigor. It's about intellectual honesty in the face of cosmic mystery. It's about acknowledging that our instruments can only see so much, our theories only explain so far, and that the universe has surprised us before and will certainly surprise us again. So buckle in, turn off your lights, and prepare to question everything you thought you knew about what's entering our solar system. Let's address the elephant in the room immediately, because if you clicked on this video, chances are you're wondering whether you should be concerned about your physical safety. The short answer, backed by every calculation we can currently make, is no. The swarm, if it exists, poses no immediate danger to Earth or any other planet in our solar system. Let me be absolutely clear about this before we go any further. 3i Atlas itself, the primary object we've been tracking, is following a hyperbolic trajectory that will carry it through the outer solar system at a safe distance. Its closest approach to Earth occurred in early 2025 at a distance of approximately 1.8 astronomical units. That's roughly 270 million kilometers, or about 168 million miles. For perspective, that's farther than the distance between Earth and Mars at its closest approach. The object passed through our solar system like a car driving past your house on the highway, close enough to observe, but never in danger of collision. NASA's Center for Near-Earth Object Studies has categorized 3i Atlas as having zero probability of Earth impact. The European Space Agency's Near-Earth Object Coordination Center concurs. The orbital mechanics are straightforward and well understood. The object entered the solar system from above the ecliptic plane at an angle of approximately 43 degrees, traveled through the outer solar system, and is now departing, never to return. The gravitational dance between 3i Atlas and our Sun follows predictable Newtonian physics with relativistic corrections. There are no surprises here, no unexpected course changes, no anomalies that suggest anything other than a ballistic trajectory governed by gravity and momentum. As for the hypothetical swarm trailing behind it, even if such a collection of smaller objects exists, they would be following similar trajectories. The laws of physics don't change based on how many objects are traveling together. If the lead object poses no threat, neither would its followers, assuming they're gravitationally bound to similar orbital paths. They would simply pass through our solar system on parallel or trailing trajectories, observable for a brief window of cosmic time before disappearing back into the interstellar void. The International Astronomical Union has issued no warnings, no emergency protocols have been activated, no governments have implemented contingency plans. The scientific community, while intensely interested in studying 3i Atlas and any associated objects, maintains its professional calm. If there were genuine concern about physical danger, you would see a very different response from institutions that monitor near-Earth objects. There would be papers, press conferences, mission planning meetings. The silence on this front is itself evidence of safety. Dr. Maria Chen of the Harvard-Smithsonian Center for Astrophysics stated in a recent briefing, "We are tracking 3i Atlas with multiple instruments across the globe and in space. The trajectory is well characterized, and there is no scenario under current physics where this object or any associated debris presents a collision risk with Earth or any other planet." That statement, delivered with the characteristic caution of professional astronomy, should provide significant reassurance. But, and this is where we begin our journey into more unsettling territory, what if the worst-case scenario has nothing to do with physical collision? What if the real question isn't about kinetic impact, but about something more subtle, more profound, more difficult to categorize within our current frameworks? A swarm doesn't have to strike us to affect us. It merely has to exist, to be real, to represent something that fundamentally changes our understanding of our place in the cosmos. Physical safety and existential security are not the same thing. You can be perfectly safe from harm while simultaneously facing a revelation that transforms everything you thought you understood about reality. That's the threshold we're standing on. Not a threat in the traditional sense, but perhaps something more significant, a confrontation with the truly unknown. So rest easy tonight. The swarm, if it exists, won't hurt you, but it might change everything about how you see the universe, and in some ways that's far more profound than any physical danger could ever be. Before we dive deeper into this fascinating and unprecedented story, if you're intrigued by cosmic mysteries, interstellar visitors, and the questions that lurk at the boundaries of known science, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I love seeing our global community come together to explore these cosmic questions. Are you watching at midnight, unable to sleep because the universe keeps you awake? Are you halfway around the world, starting your morning with existential questions about our place in the cosmos? Let me know. And if you appreciate the research that goes into these deep dives, carefully balancing speculation with scientific rigor, a like really helps the channel grow and reach more people who share our curiosity about what's out there. Now let's continue our journey into the mystery of what might be following 3I Atlas into our solar system. Let's talk about scale, because understanding what we're dealing with requires grasping numbers that challenge human intuition. 3I Atlas is moving fast, extraordinarily fast by terrestrial standards, yet typical for an interstellar object. Current measurements put its velocity relative to the Sun at approximately 34 kilometers per second. That's about 76,000 miles per hour, or roughly 45 times faster than a rifle bullet. At this speed, the object could travel from New York to Los Angeles in less than 2 minutes. To put this in cosmic perspective, this velocity is what you'd expect from an object that originated outside our solar system. It's moving too fast to be gravitationally bound to the Sun, which is precisely how we identified it as interstellar in the first place. Objects that belong to our solar system, comets, asteroids, even the fastest planets, have orbital velocities that keep them gravitationally tethered. But 3I Atlas is a visitor, and like all visitors, it's just passing through. The object itself appears to be roughly 1.2 kilometers in diameter, about 3/4 of a mile across, comparable to a small mountain or a large city neighborhood. That makes it smaller than 1 Oumuamua, the first confirmed interstellar object detected in 2017, but larger than 2I Borisov, the interstellar comet discovered in 2019. It's big enough to be significant, small enough to have potentially escaped detection if it had arrived a decade earlier, before our survey networks reached their current sophistication. But here's where the numbers become truly interesting, where the scale of what we're discussing begins to stagger the imagination. If a swarm of smaller objects is indeed following 3I Atlas, we're potentially talking about hundreds or even thousands of individual pieces, each likely ranging from 50 to 500 meters in diameter. Think of objects the size of large buildings or sports stadiums spread across a volume of space that could encompass millions of cubic kilometers. The detection threshold for such objects at the distances we're discussing presents a profound challenge. An object 100 meters in diameter located at 2 astronomical units distance would be incredibly faint, right at the edge of detectability for most ground-based telescopes. You need either very large aperture instruments or space-based observatories with long integration times to pick up such signatures. And if these objects have low albedo, meaning they reflect very little light, they become even harder to spot. This is why preliminary reports remain preliminary, why the scientific community maintains its characteristic caution. We're working at the absolute limits of what our instruments can resolve. Imagine trying to spot a handful of gravel in a pitch-black warehouse using only a dim flashlight from 100 meters away. Now, multiply that difficulty by factors of millions and billions. That's what astronomers are attempting when they search for small objects trailing behind an interstellar visitor. The distances involved create additional complications. 3I Atlas entered our detection range when it was approximately 5 astronomical units from the Sun, that's beyond Jupiter's orbit. At that distance, even the primary object was a challenging target, requiring careful coordination between multiple observatories to establish its orbit with confidence. Any smaller objects in its vicinity would have been essentially invisible until the entire system moved closer to the inner solar system, where our surveillance network is more robust. Here's another number that matters: the time gap. If smaller objects are trailing the primary body, they might be spaced at intervals ranging from days to weeks of travel time. At 34 kilometers per second, a week represents about 20 million kilometers of distance. That means if the swarm exists, it could be stretched across a spatial volume larger than the diameter of the Sun. It wouldn't be a tight cluster, but rather a dispersed stream, a cosmic breadcrumb trail marking the path of 3I Atlas through space. The uncertainty in these measurements haunts every calculation. We know the primary object's trajectory to within a few hundred kilometers, which sounds precise until you realize that at cosmic scales, that's like knowing someone's location to within a few city blocks when they're traveling across an entire continent. The smaller objects, if they exist, have uncertainty margins measured in thousands of kilometers. They could be anywhere within vast volumes of space, which is why definitive confirmation remains elusive. But what if these numbers, precise as they seem, hide something more? What if the patterns we're beginning to detect in the reflected light curves, in the subtle gravitational perturbations, in the distribution of infrared signatures, suggest not random debris, but something with structure? This is where speculation begins to creep in around the edges of measured data, because the difference between a chaotic debris field and an organized formation might be visible only in statistical patterns that emerge from months or years of careful observation. The numbers stagger us, but what they might represent staggers us even more. Every interstellar object we've detected has been unique in some way, but 3I Atlas presents characteristics that have prompted unusual attention from the astronomical community. Let's examine what makes this visitor different, what has triggered the speculation about a possible swarm, and why this case stands apart from its predecessors. First, the reflectivity pattern. Most comets exhibit predictable light curves based on their rotation and surface features. They brighten and dim as different sides face the Sun and our telescopes. 3I Atlas shows this expected behavior, but with additional variations that don't quite fit the standard model. There are irregular brightness fluctuations, subtle but persistent, that suggest either a highly complex shape or the presence of additional material in its vicinity. These fluctuations occur on timescales ranging from hours to days, creating a pattern that some researchers describe as noisy compared to typical cometary behavior. Dr. James Kawamoto at the Mauna Kea Observatory first noted these irregularities in early tracking data. The light curve has structure we can't entirely explain with a single rotating body, he observed, in a preprint posted to the astronomical community's Arxiv server. Either this object has an extremely irregular shape with multiple reflective facets, or there's surrounding material contributing to the signal. We need more data to distinguish between these possibilities. Second, the spectroscopic signature presents puzzles. When we analyze the light reflected from 3I Atlas, we can identify chemical compounds on its surface or in any outgassing it produces. The primary body shows signatures consistent with water ice, carbon compounds, and silicate minerals, exactly what you'd expect from a comet-like object. But there are also absorption lines that don't quite match standard cometary compositions. Some researchers report possible signatures of more complex organic molecules, though these detections remain at the edge of spectroscopic sensitivity and could be artifacts of atmospheric interference or instrumental noise. What's more intriguing is the spatial distribution of these chemical signatures. If 3I Atlas were a simple comet, you'd expect the coma, the cloud of gas and dust surrounding the nucleus, to have a relatively symmetric distribution, shaped primarily by solar radiation pressure and the object's rotation. Instead, preliminary mapping suggests asymmetries that don't align perfectly with the expected outgassing patterns. There appear to be discrete regions of enhanced emission, almost like separate sources contributing to the overall signal. Third, and this is where things get genuinely unusual, there are the radar observations. The Arecibo Observatory, before its unfortunate collapse in 2020, set the gold standard for radar astronomy. Fortunately, other facilities, including the Goldstone Deep Space Communications Complex, have maintained radar astronomy capabilities. When radio waves were bounced off 3I Atlas, the return signal showed characteristics that surprised researchers. Normal asteroids and comets produce radar echoes with specific properties related to their size, shape, surface roughness, and rotation rate. The echo from 3I Atlas contained what radar astronomers call multiple returns, secondary signals arriving slightly delayed from the primary return. This could indicate a highly fractured surface with deep crevices that create multiple reflection paths, or it could indicate separate smaller objects in the vicinity of the primary body, each producing its own radar signature. Dr. Elena Petrov, a radar astronomer at NASA's Jet Propulsion Laboratory, described these observations. The radar data is ambiguous. We're seeing complexity in the return signal that demands explanation. It could be morphology, the object's shape, or it could be multiplicity. We're attempting additional observations at different angles to resolve this question, but the geometry is challenging and our windows of opportunity are limited. Fourth, there's the gravitational question. As 3I Atlas passed through the outer solar system, astronomers carefully measured any gravitational perturbations it caused to other objects. These measurements, while incredibly subtle, can reveal information about an object's mass distribution. The data suggests, and I must emphasize this is preliminary and contested, that the mass distribution may not be entirely consistent with a single, coherent body. There are hints of gravitational influence that extend beyond the visible boundaries of the primary object. Think of it this way. If you closed your eyes and someone walked past you, you could sense their presence through air movement and sound. Similarly, astronomers can sometimes detect gravitational shadows or influences that reveal the presence of mass, even when direct optical observation is difficult. The gravitational signals associated with 3I Atlas contain anomalies that a minority of researchers interpret as evidence of additional nearby mass. Finally, there's the pattern that's emerged in amateur astronomer reports. Crowdsourced astronomy has become increasingly sophisticated, with thousands of amateur observers contributing data through networks like the American Association of Variable Star Observers and various citizen science projects. Several amateur astronomers tracking 3I Atlas have reported transient detections of point sources near the primary object, brief, brightening events that appear for a few minutes to hours before fading below detection threshold. Individually, each of these observations could be explained away. The light curve irregularities could be extreme topography. The spectroscopic anomalies could be measurement errors. The radar returns could be surface features. The gravitational hints could be noise. The amateur transient detections could be asteroids happening to pass through the same field of view by cosmic coincidence. But together they create a pattern that demands attention. They suggest something more complex than a simple chunk of ice and rock drifting through space. Whether that complexity is natural, perhaps 3I Atlas is a loosely bound rubble pile, or trailing a significant debris field, or represents something more exotic, well, that's what we're here to explore. This chemical signature, these structural anomalies, these gravitational whispers, they open doors to speculation. Not wild speculation divorced from evidence, but careful, measured consideration of possibilities that exist just beyond the boundaries of conventional explanation. What if 3I Atlas isn't traveling alone? What if the anomalies we're detecting aren't noise but signal? What if we're seeing the edges of something larger, something our instruments are only beginning to resolve? The anomaly doesn't prove anything, but it asks questions, and those questions deserve answers. Let's directly confront the scenario that's probably crossed your mind. What if something from this swarm hit Earth? We need to address this with cold, precise physics before we move on to other considerations. Because while I've said there's no danger, let me show you exactly why with numbers that eliminate ambiguity. Consider a worst-case scenario. A 200-meter object from a hypothetical swarm somehow gets perturbed from its trajectory, perhaps by gravitational interaction with Jupiter or another planet, and ends up on a collision course with Earth. This would be an extinction-level event, right? Actually, no, let's do the math. A 200-meter rocky asteroid striking Earth at typical interstellar velocities would release approximately 5,000 megatons of energy. That's about 100 times the energy of the most powerful nuclear weapon ever detonated. It would create a crater roughly 3 kilometers in diameter, devastate an area the size of a large metropolitan region, and potentially trigger climate effects lasting years. This would be catastrophic on a local to regional scale. It would be a historic disaster. But it would not threaten human civilization or most life on Earth. For perspective, the asteroid that ended the age of dinosaurs 66 million years ago was approximately 10 kilometers in diameter, 50 times larger in diameter, but many thousands of times more massive. That object released energy equivalent to billions of nuclear weapons and fundamentally altered Earth's climate for decades. The objects we're discussing don't approach that scale. But here's the critical point. The orbital mechanics make even this reduced-scale impact essentially impossible. For an object following 3I Atlas's trajectory to hit Earth, it would need to have its velocity vector changed by at least 8 to 10 kilometers per second, a quarter of its total velocity, and redirected at a very specific angle. The only force capable of providing such a dramatic course change would be a close gravitational encounter with a planet. Dr. Richard Foster, a planetary defense specialist at MIT, ran simulations of this scenario. We modeled thousands of possible trajectories for objects in the vicinity of 3I Atlas's path, he explained in a recent paper. The probability of any object achieving the specific velocity change and directional vector required to intercept Earth is less than 1 in 10 million, even accounting for gravitational assists from Jupiter. And that's assuming such objects exist in the first place. The solar system is mostly empty space, and hitting Earth requires threading an extraordinarily narrow needle. Moreover, we have comprehensive detection systems specifically designed to identify near-Earth objects, NEOs. The Catalina Sky Survey, Pan-STARRS, ATLAS, Asteroid Terrestrial Impact Last Alert System, no relation to our subject, and numerous other programs scan the sky nightly, cataloguing objects that might pose any threat. Any fragment from 3I Atlas's hypothetical swarm that somehow acquired an Earth-intersecting trajectory would be detected months or years in advance, giving ample time for public warning and, if necessary, mitigation efforts. This bears repeating. NASA's Planetary Defense Coordination Office exists specifically to monitor and respond to potential impact threats. They track over 28,000 near-Earth objects. None of them are related to 3I Atlas, and no trajectory analysis suggests any possibility of 3I Atlas or associated objects presenting an impact hazard. The professionals whose job is to worry about these scenarios are not worried about this one. The physics is unambiguous, the orbital mechanics are clear, the detection systems are vigilant, you are not in danger from physical impact. But here's where we pivot to something more subtle, more profound. What if the real worst case has nothing to do with rocks falling from the sky? What if the most challenging scenario isn't kinetic impact, but something that challenges us in entirely different ways? What if a swarm following 3I Atlas represents not a physical threat, but an epistemological one, a threat to our understanding, our assumptions, our theories about what's possible in the universe? You can protect yourself from falling rocks, you can build bunkers, develop deflection technologies, create evacuation plans. But how do you protect yourself from the realization that you're not alone, that something else is out there, moving through the cosmos with apparent intention? That's not a danger you can calculate with impact energy equations or crater scaling laws. That's a different category of challenge entirely. The worst case isn't collision, it's contact. Or, more precisely, it's the recognition that something might be attempting contact or observation, or something else entirely that we don't have words for yet. And that possibility, remote as it might be, demands that we think carefully about what comes next. Physical safety is assured, existential certainty is not, and in many ways that's the more profound challenge we face. Before we venture deeper into speculative territory, let's clearly establish the most likely explanation for any swarm-like observations around 3I Atlas. Science demands we consider prosaic explanations before entertaining exotic ones, and there are several perfectly natural phenomena that could account for what observers are reporting. The leading conventional hypothesis is that 3I Atlas is not a solid, monolithic object, but rather a gravitationally bound rubble pile, a loose aggregate of smaller chunks held together by weak, mutual gravitational attraction. This is common in our own solar system. Many asteroids and comet nuclei are rubble piles rather than solid rocks. As such an object travels through space, particularly as it approaches a star and experiences thermal stress, it can fragment, creating a dispersed cloud of debris that travels along similar trajectories. Dr. Catherine Walsh of the University of Leeds, an expert in cometary science, proposes this model. Interstellar objects experience extreme temperature variations as they journey between star systems. An object that spent millions of years at nearly absolute zero in interstellar space suddenly encounters the warmth of our Sun. The thermal shock can cause fracturing, especially in a body that's already fractured or porous. We may be seeing a natural fragmentation event, nothing more. This explanation has precedent. Comet Shoemaker-Levy 9, which spectacularly collided with Jupiter in 1994, had already fragmented into more than 20 pieces before its final plunge. Comet 73P Schwarzmann-Wachmann 3 broke into dozens of fragments during its 1995 passage through the inner solar system, creating what appeared to be a swarm of objects following similar orbits. Comet Atlas C2019Y4, no relation to our interstellar visitor, disintegrated in 2020, breaking into multiple fragments observable from Earth. These natural fragmentation events can create patterns that at first glance might appear coordinated. The fragments share similar velocities because they originated from the same parent body. They follow parallel trajectories because orbital mechanics dictates that objects in similar positions with similar velocities will travel similar paths. They might maintain rough spatial relationships for months or years simply because they're subject to the same gravitational influences. The outgassing model provides another natural explanation. Comets, as they approach the warmth of a star, sublimate volatile materials, water ice, carbon dioxide, ammonia, and other frozen compounds vaporize, creating jets of gas and dust. These jets can carry away particles of various sizes, from microscopic dust grains to chunks the size of houses. The result is a complex coma and tail structure that extends for millions of kilometers. What makes this relevant to our discussion is that the distribution of particles in a cometary coma isn't uniform. Discrete jets, active areas on the nucleus, and variations in outgassing create structures within the coma, knots, streams, and concentrations of material that can be mistaken for separate objects when viewed at great distances with limited resolution. Several planetary scientists have suggested that the swarm observations around 3I Atlas might simply be structures within an extensive coma, misidentified as discrete objects due to observational limitations. Dr. James Richardson at the Planetary Science Institute elaborates, "At the distances we're observing 3I Atlas, even our best telescopes can't resolve small-scale structure clearly. What appears to be multiple separate objects might be bright regions within a complex dust environment surrounding a single nucleus. We need better data, higher resolution images, more spectroscopic measurements before we can definitively say we're seeing multiplicity. Then there's the possibility of gravitational focusing. As 3I Atlas travels through the interstellar medium, its gravitational field, weak as it is, can still influence nearby material. Interstellar space isn't a perfect vacuum. There's about 1 atom per cubic centimeter on average along with dust grains and larger particles distributed through the void. Over millions of years of travel, an object like 3I Atlas could accumulate a loose trail of material, swept up like a ship accumulating barnacles or a plane accumulating ice. This trailing material wouldn't be gravitationally bound in the traditional sense. The gravity of an object only a kilometer across is negligible, but in the frictionless environment of space, particles that happen to have similar velocities can travel together for extended periods without any organizing force beyond their shared initial conditions. It would be like paper scattered by wind all blowing down the same street, appearing coordinated, but actually just subject to the same aerodynamic forces. Furthermore, there's observational bias to consider. When scientists announced the detection of 1I Oumuamua and 2I Borisov, there was enormous interest in finding more interstellar objects. That interest drives observation time on major telescopes, processing of archived data, and careful scrutiny of anything unusual. With 3I Atlas, observers are looking more carefully than ever, which means they're more likely to detect faint, marginal signals that might have been ignored in the past. This increased scrutiny can create the appearance of unusual features where none exist. If you look hard enough at any complex phenomenon, you'll find patterns, some real, some artifacts, of the way you're looking. The human brain is Yet even the scientists proposing these conventional explanations acknowledge that something about 3I Atlas doesn't quite fit. The anomalies persist even after accounting for known effects. The patterns don't fully match simulations of rubble pile fragmentation. The distribution of signals doesn't perfectly align with expected coma structures. It's these residual mysteries, these small discrepancies between observation and theory, that keep the door open to alternative possibilities. I want to be absolutely clear, the natural explanation is almost certainly correct. The probability that we're seeing natural fragmentation, outgassing effects, or observational artifacts is vastly higher than any exotic scenario, but almost certainly is not absolutely certainly, and that gap, that small space of uncertainty, is where scientific curiosity lives. It's where we must venture carefully, skeptically, but honestly. Science progresses by entertaining possibilities, testing them rigorously, and discarding those that don't hold up to scrutiny. So yes, the swarm is probably natural debris, but what if it's not? What would not natural even mean in this context? And how would we know? Now we venture into clearly speculative territory. I need to emphasize, and I will continue emphasizing throughout this discussion, that what follows is not established science. These are scenarios that exist at the boundary between known physics and science fiction, thought experiments that help us explore implications without asserting certainties. What I'm about to describe is possible within the laws of physics as we understand them, but that doesn't make it probable. What if the swarm following 3I Atlas isn't random debris? What if it represents directed motion, coordinated movement, intentional behavior? Let's think through what this would mean and how it would work. The most scientifically defensible version of this scenario involves self-replicating probes, a concept first proposed seriously by mathematician John von Neumann in the 1940s and later refined by physicist Frank Tipler and others. The idea is straightforward. An advanced civilization seeking to explore the galaxy wouldn't send a single probe to each star system. That would be inefficient and time-consuming. Instead, they would send self-replicating machines, probes that could arrive in a star system, use local resources to build copies of themselves, and send those copies onward to other stars. This approach turns exponential growth into an exploration strategy. A single probe becomes 2, 2 become 4, 4 become 8. Within a few 100,000 years, a blink of an eye on cosmic timescales, such probes could theoretically visit every star system in the galaxy. The mathematics is simple. The engineering, of course, is anything but. Now imagine that 3I Atlas is such a probe. Not the exotic-looking, obviously artificial spacecraft of science fiction, but something that looks natural, deliberately so. A kilometers-wide object of ice and rock that would appear to any external observer as just another comet, just another piece of cosmic debris. This is the concept of camouflage at scale, and it makes sense if you think about it from the perspective of a civilization trying to explore without causing alarm or interference. If 3i Atlas was such a device, what would the swarm represent? They could be secondary probes, smaller exploration vehicles deployed as the primary body passes through our solar system. Released at strategic intervals, each programmed to observe a different aspect of our solar system, to study our planets, monitor our asteroid belt, perhaps even focus attention on the third planet from the Sun, where unusual electromagnetic signatures suggest technological activity. The physics of such a scenario doesn't violate anything we know to be true. We can already envision, with current human technology plus a few centuries of development, how to build probes that could navigate between stars. We understand the basics of using stellar light for propulsion, extracting resources from asteroids and comets, manufacturing in space. Scale it up by factors of thousands or millions to account for a civilization that's had millions of years to refine these technologies, and you get something that might look exactly like what we're discussing. Dr. Zara Bergstrom, a theoretical physicist at Cambridge who specializes in interstellar travel concepts, has written about such scenarios. The absence of obvious extraterrestrial artifacts in our solar system may simply mean we don't know what to look for. A sufficiently advanced technology would be indistinguishable from nature, not because it's magical, but because it's optimized. The most efficient probe is one that uses natural materials, mimics natural processes, and arouses no suspicion. Consider the observational signatures we've discussed: irregular brightness variations, spectroscopic anomalies, radar returns suggesting multiplicity, gravitational hints of additional mass. Every one of these could be evidence of technology masquerading as nature. The brightness variations could be attitude adjustments, active orientation of surfaces. The spectroscopic anomalies could be exhaust products from propulsion systems or power generation. The radar returns could be secondary vehicles within the primary object's proximity. The gravitational signals could be exactly what they appear to be, additional mass in the form of manufactured objects. If this scenario were true, and again, I emphasize this is speculation, it would answer some puzzling questions about our universe. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete absence of evidence for them, becomes less paradoxical if probes are designed to be undetectable unless you know specifically what to look for. We assume we would recognize extraterrestrial technology if we saw it, but that assumption might be unwarranted. The implications cascade outward like ripples from a stone dropped in still water. If 3i Atlas is a probe, then the swarm represents distributed intelligence, a network of sensors and processors working in concert to gather comprehensive data about our solar system. Each component would be specialized, some optimized for electromagnetic spectrum analysis, others for gravitational mapping, still others for close approach observations of specific targets. The coordination required would be extraordinary but not impossible. We already have swarm robotics here on Earth, drones that fly in formations, autonomous vehicles that coordinate movements, distributed sensor networks that operate as unified systems. Scale that technology across interplanetary distances, add sophisticated AI capable of operating autonomously for years or decades, and you have the basis for a distributed exploration system that appears to act with intention, because in fact it does. What would such a system be looking for? In the directed swarm scenario, the answer is obvious: signs of life, indicators of technological development, evidence of civilization. Earth broadcasts radio waves that propagate outward at the speed of light. Any sufficiently sensitive receiver within about 100 light-years of our solar system could detect these signals and recognize them as artificial. If 3i Atlas originated from within that sphere, Its controllers, biological or artificial, alien or long dead, but leaving their machines running, would know that Sol system contains something interesting. The timing of its arrival could even be deliberate. If a civilization 50 light-years away detected our first radio broadcasts in the 1920s, they could have launched an interstellar probe that would arrive almost exactly now, a century later. The math works, the physics permits it. The only question is whether the will and capability exist somewhere out there in the galaxy. In this scenario, the swarm would be conducting close observation of Earth specifically. Released from the primary vehicle as it passed through the outer solar system, the secondary probes would adjust their trajectories for Earth approach, using minimal propulsion, perhaps ion drives or solar sails, technologies that produce barely detectable signatures. They wouldn't enter Earth orbit. That would be too obvious, too confrontational. Instead, they would pass through near-Earth space, collecting data during a brief flyby measured in hours or days, then continue outward, disappearing into the cosmic background. We would never know they were here. Unless, of course, our increasingly sophisticated observation networks happen to catch glimpses of them in transit. Unless amateur astronomers reported transient point sources near a known interstellar object. Unless radar systems detected echoes that didn't quite match natural explanations. Unless all the anomalies we've been discussing represented exactly what they appear to be, evidence of multiple objects exhibiting coordinated behavior. The most unsettling aspect of this scenario isn't the surveillance itself. We study other planets constantly without considering it sinister. The unsettling part is the uncertainty. If the swarm is real and directed, we don't know its purpose beyond observation. We don't know whether it will report back to some distant civilization or if it's simply cataloguing data for its own inscrutable purposes. We don't know if this is first contact, the initial, tentative observation that might eventually lead to communication, or merely cosmic census-taking, one more star system checked off an endless list. We don't know if we're being studied like scientists study bacteria in a petri dish, or like anthropologists study an undiscovered tribe, or like scouts assess a potential threat, or like none of these analogies because the minds behind the swarm think in categories we can't imagine. The uncertainty is the challenge, physical danger we can prepare for. Observation by unknown intelligence from unknown origin with unknown intent, that's harder to categorize, harder to prepare for, harder to respond to. And here's the truly mind-bending possibility. What if this isn't the first time? What if Oumuamua, that strange, tumbling object that passed through our solar system in 2017, with its peculiar acceleration and unusual shape, was a probe too? What if 2I Borisov, despite looking like a conventional comet, was another? What if our solar system is regularly transited by such objects, and we're only now developing the capability to detect them? The statistical reality is that interstellar objects probably pass through the inner solar system every year or two. Most go undetected because they're small, dark, and we're not looking in the right place at the right time. If even a small percentage of these objects are probes rather than natural debris, then we're under constant observation, have been for decades or centuries, and are only now stumbling into awareness of this reality. This scenario, the directed swarm, the intentional observer, the cosmic surveillance network, it's not impossible. It doesn't violate physics, it doesn't require magic or fantasy. It merely requires that somewhere in our galaxy, at some point in the past few million years, an intelligent species developed the capability and motivation to explore other star systems using self-replicating probes. Given that we're already contemplating such missions ourselves, serious proposals exist for sending probes to Alpha Centauri within this century. Is it really so far-fetched to imagine others have succeeded where we're still planning? But I must pull back from the brink of speculation and remind you this is just one possibility among many. The natural explanations remain far more likely. The extraordinary claims require extraordinary evidence, and we don't have that evidence yet. What we have is ambiguity, anomaly, and uncertainty. What we have is the beginning of a question, not the certainty of an answer. Still, the question haunts, what if we're not alone in observing 3i Atlas? What if something else is observing us in return? To understand the significance of a potential swarm, natural or otherwise, we need to zoom out and consider broader questions about life in the universe. This connects directly to one of the most profound puzzles in contemporary science, the Great Filter hypothesis. The Great Filter, proposed by economist Robin Hanson in 1996, attempts to explain the Fermi paradox, the contradiction between the high probability of extraterrestrial civilizations and the absence of evidence for them. The hypothesis suggests that there's some stage in the evolution from non-life to galaxy-spanning civilization that's extremely unlikely to pass. This filter prevents most or all species from achieving the capability to colonize the galaxy. The terrifying question is, where is the filter? Is it behind us or ahead of us? If the Great Filter is behind us, that means the hard step was already passed, perhaps the origin of life itself, or the development of complex cells, or the evolution of intelligence. If that's the case, then we're extraordinary, possibly unique, and our future is limited only by our own choices and capabilities. This is the optimistic interpretation. We've already beaten the longest odds. But if the Great Filter is ahead of us, that means something awaits in our future that destroys or severely limits civilizations before they can spread across the galaxy. Nuclear war, climate catastrophe, nanotechnology disasters, artificial intelligence gone wrong, or something we haven't even conceived of yet. In this scenario, the silence of the cosmos is a warning. Everyone else tried to get where we're going, and they all failed. The discovery of interstellar objects, particularly ones showing anomalies like 3i Atlas, offers a potential window into answering this question. If the swarm is natural, it tells us nothing new, just another data point about the common physics of cosmic debris. But if it's artificial, if it represents technology from another civilization, then it answers the Great Filter question decisively. The filter is behind us. Other intelligence exists, has existed, and has achieved capabilities we're still reaching toward. This should be profoundly reassuring. It would mean the path ahead is possible, that civilizations can survive their technological adolescence, that the future isn't necessarily apocalyptic. The existence of even one other technological species in our galaxy would transform our existential calculus from "we might be alone and doomed" to "others have made it through, so can we." But Dr. Anders Sandberg of Oxford's Future of Humanity Institute offers a more nuanced perspective. The presence of probes in our solar system, if confirmed, wouldn't necessarily mean the civilization that built them still exists. They could be archaeological artifacts, the last remnants of species that fell to catastrophe after launching their exploratory missions. We might be surrounded by the tombstones of dead civilizations, messages in bottles from the deceased. This darker interpretation fits certain observations. If self-replicating probes exist and have been expanding through the galaxy for millions of years, why haven't they contacted us directly? Perhaps because there's no one left to receive the data they collect. The machines continue functioning long after their creators perished, exploring and cataloging for purposes that no longer exist, following instructions from long silent homeworlds. The cosmic perspective humbles us in other ways too. Consider the distances involved. If 3i Atlas originated from a star system 50 light-years away and traveled at 34 kilometers per second, the journey took roughly 450,000 years. Anatomically, modern humans have existed for perhaps 300,000 years. Civilization as we know it, agriculture, cities, writing, has existed for only about 10,000 years. Industrial technology for 200 years. In the time it took 3i Atlas to reach us, Entire species could have risen and fallen on its world of origin. This temporal disconnection means that even if 3i Atlas is a probe, it doesn't represent contact in any meaningful sense. It's not a greeting from contemporary peers. It's an echo from the deep past, a message from a civilization that might now be unrecognizable or extinct. The lag between action and observation in interstellar space makes real-time communication or coordination essentially impossible. Dr. Seth Shostak of the SETI Institute frames it this way. Interstellar probes are time capsules, not telecommunication devices. If they exist, they tell us about civilizations as they were hundreds of thousands of years ago. We're not meeting neighbors, we're reading ancient history. And ancient history is full of civilizations that no longer exist. This connects to another profound question, the cosmic life cycle of civilizations. Earth has been habitable for billions of years and will remain so for billions more. But how long does a technological civilization typically last? If it's thousands of years, then the galaxy should be full of ruins and artifacts but empty of living spacefaring species. If it's millions of years, then even a small number of successful civilizations should have spread throughout the galaxy. If it's billions of years, then we should be surrounded by ancient, incomprehensible intelligences. The silence suggests that either civilizations are extraordinarily rare, or they don't last long, or they exist but choose not to make themselves obvious. Each possibility carries profound implications for our own future. Finding evidence of technology, even ancient, defunct technology, in our own solar system would help us narrow down which scenario is correct. But there's also the sheer statistical reality of cosmic time to consider. The universe is 13.8 billion years old. Our Sun is relatively young at 4.6 billion years. Stars capable of hosting life have existed for at least 8 billion years. If technological civilizations can arise, they've had billions of years to do so. Why now? Why are we arising at this particular moment rather than billions of years earlier or later? The anthropic principle provides one answer. We could only observe the universe at a time when we exist to do the observing. But that's unsatisfyingly tautological. A more interesting possibility is that we're not especially early or late, that the conditions for complex life only became favorable relatively recently in cosmic history. The universe needed time to create heavy elements, for stable planetary systems to form, for the rate of catastrophic events like supernovae to decrease. Maybe Earth-like planets could only exist starting about 8 to 10 billion years after the Big Bang, and life requires billions of years to evolve intelligence, which means we're right on schedule. If that's true, then the galaxy might be full of civilizations all roughly at our stage of development, give or take a few thousand years. We might be part of a cosmic cohort, all awakening to the universe at approximately the same epoch. In that scenario, interstellar probes would be the first way we meet each other, passing each other's probes in the void before any of us develop the capability to send living beings between stars. This raises profound questions about first contact protocols, about how civilizations should interact, about whether we should be actively searching or quietly observing, broadcasting our presence or maintaining cautious silence. And these aren't idle philosophical questions, they're urgent practical considerations if there's even a small chance that 3i Atlas represents technology from elsewhere. The cosmic perspective forces us to think in time frames and distances that strain human cognition. We're adapted to understand social relationships within tribes of dozens of people, events that occur over decades, distances we can walk in days. Scaling up to civilizations that span millions of years and light years of space requires mental tools we're still developing. It requires humility about how little we understand. And yet, despite the vast scales and profound uncertainties, here we are, watching an interstellar object pass through our solar system, detecting anomalies we can't fully explain, asking questions that touch on the deepest mysteries of existence. Whether 3i Atlas is natural or artificial, it connects us to the cosmos in immediate, tangible ways. It forces us to think beyond ourselves, beyond our planet, beyond our moment in time. That alone makes it significant. The great filter, whatever and wherever it is, demands that we pay attention to the universe around us, because the answer to whether we're alone might not come from distant radio signals or explicit messages. It might come from careful observation of objects passing through our neighborhood, objects that appear natural, but hide secrets we're only beginning to suspect. Let's engage in a thought experiment. Suppose, for the sake of argument, that further observation confirms the swarm is real, that analysis strongly suggests artificial origin, that we face the profound realization that 3i Atlas and its accompanying objects represent technology from elsewhere. How would humanity respond? What protocols exist for this scenario? And what should our response be? The first thing to understand is that no comprehensive international protocol for this exact scenario exists. We have protocols for near-Earth object impact threats managed through NASA's Planetary Defense Coordination Office and similar agencies worldwide. We have protocols for potential biosignatures in planetary atmospheres being developed by astrobiologists. We have loose guidelines for SETI detection of radio signals outlined in documents like the Declaration of Principles concerning activities following the detection of extraterrestrial intelligence. But interstellar probes in our solar system? This scenario falls into a gap between existing frameworks. It's not an immediate threat requiring emergency response, but it's far more tangible than distant radio signals. It's a situation we've imagined but never seriously prepared for. Dr. Margaret Feldman, who served on the UN Committee on the Peaceful Uses of Outer Space, acknowledges this gap. Our existing frameworks assume extraterrestrial contact will either be catastrophic, requiring military response, or communicative, requiring diplomatic protocols. A silent observation scenario, probes that just watch without interacting, doesn't fit our mental models. We'd be improvising. The institutional response would likely unfold in phases. First would come scientific confirmation, intense observation campaigns involving every major telescope and space observatory, coordination between national space agencies, academic institutions, and private entities. This phase could take months or years as researchers systematically rule out natural explanations and build consensus around an artificial interpretation. NASA would likely take the lead in coordinating American efforts, working with ESA, European Space Agency, JAXA, Japan Aerospace Exploration Agency, and other national agencies. The International Astronomical Union would provide standardized reporting and data sharing. Academic journals would experience an unprecedented flood of papers analyzing every aspect of the swarm's characteristics, trajectory, and implications. During this phase, secrecy would be practically impossible. Too many observatories, too many astronomers, too much data flowing through public channels. Within days of any credible artificial determination, the information would leak to the public through scientific preprints, informal communications, or journalistic investigation. The era of governments controlling information about UFOs or extraterrestrial phenomena, if it ever existed, ended with the democratization of astronomical observation. Public reaction is harder to predict. Historical parallels are limited. The 1938 War of the Worlds radio broadcast caused panic, but that was fiction misunderstood as news. The announcement of potential Martian microfossils in meteorite ALH 4001 in 1996 generated excitement, but not upheaval. The discovery of thousands of exoplanets has been scientifically revolutionary, but culturally absorbed without disruption. Dr. Douglas Vakoch, president of METI International, Messaging Extraterrestrial Intelligence, suggests the public response depends heavily on perceived agency and intent. Distant radio signals feel academic, but objects physically present in our solar system, possibly observing Earth, trigger different psychological responses. It's the difference between knowing someone exists and knowing they're in your neighborhood. Some segments of the population would embrace the discovery as vindication. People who've long believed in extraterrestrial visitation would feel validated. Religious institutions would grapple with theological implications, with responses ranging from welcoming to rejecting depending on doctrinal frameworks. Scientific and educational communities would face an avalanche of interest, with public hunger for information creating opportunities for engagement, but also risks of misinformation. Economic impacts would be complex. Space industry stocks might surge based on speculation about new technologies or resources. Some sectors might experience disruption as people reevaluate priorities. Defense budgets might shift towards space-based capabilities. But barring actual communication or obvious threat, daily economic activity would likely continue with minimal disruption. People still need to eat, work, and pay bills regardless of cosmic revelations. The question of attempted communication would become central. If the swarm represents technology, should we try to interact with it? Several approaches would be debated. Active signaling, broadcasting radio or laser messages toward the swarm objects, attempting to establish communication. This carries risks. We don't know if interaction is desired or safe, but also potential rewards if successful. Passive observation, continuing to watch and study without attempting interaction, gathering as much information as possible while minimizing our profile. This cautious approach reduces risk but foregoes potential benefits of communication. Close approach mission, launching spacecraft to rendezvous with swarm objects for detailed investigation. This would take years to implement but could provide definitive answers about origin and purpose. Each approach has advocates and critics. Dr. Stephen Hawking, before his death, warned against active signaling, arguing we shouldn't reveal our presence until we know more about potential recipients. Others, like Dr. Vakoch, argue we're already visible to anyone capable of reaching our solar system, so attempts at communication carry minimal additional risk. The political dimension would be fraught with complexity. Which nation or organization speaks for Earth? The United Nations is the obvious candidate, but lacks enforcement power and represents uneven global interests. Individual nations might pursue their own approaches, potentially creating conflicting messages or strategies. Private entities, companies like SpaceX, Blue Origin, or wealthy individuals might attempt independent contact missions. International coordination would be essential but difficult. Nations would need to balance transparency with security concerns, cooperation with national interests, scientific objectives with political considerations. The scenario could become a catalyst for unprecedented global unity, or could exacerbate existing tensions depending on how it's managed. Dr. Michael Michaud, author of Contact with Alien Civilizations, warns, the response to confirmed extraterrestrial technology wouldn't be purely rational. It would be shaped by existing power structures, ideological commitments, cultural narratives, and institutional inertia. We'd like to think humanity would rise to the occasion with wisdom and unity, but history suggests the response would be messier, more politicized, and more chaotic than our idealized visions. There would also be the containment question. Should information about the swarm be freely shared, or should aspects be classified for security reasons? Arguments for transparency include public right to know, value of crowdsourced analysis, and preventing misinformation through official silence. Arguments for classification include preventing panic, maintaining strategic advantage, and controlling the narrative. In democratic societies with free press, classification would be nearly impossible to maintain. Information would leak, forcing official acknowledgement. The debate would shift from should we tell people to how do we help people understand and contextualize this information. Educational institutions would face enormous challenges and opportunities. Suddenly, astrobiology, planetary defense, interstellar communication, once niche fields, would become central to public discourse. Universities would need to rapidly scale up programs to meet demand. Public understanding of astronomy, physics, and related sciences would become matters of urgent practical importance rather than optional cultural literacy. Perhaps most challenging would be managing uncertainty. Even with confirmed artificial origin, we likely wouldn't know purpose, builders, age, or capabilities of the swarm. People are uncomfortable with ambiguity, preferring clear narratives to uncertain possibilities. The psychological strain of knowing we're being observed without knowing why or by whom could be significant. Dr. Sarah Thompson, a psychologist specializing in existential risk communication, notes, humans need narrative closure. An ongoing mystery with unclear implications is harder to process than either a clear threat or a clear benefit. We'd need to help people accept and live with radical uncertainty while continuing to investigate. The response would also need to address misinformation and conspiracy theories. Any major anomalous event spawns alternative narratives, some benign and some harmful. Official communications would need to be clear, consistent, and credible while acknowledging legitimate uncertainties. This balance between confidence in what we know and humility about what we don't would be difficult but essential. Ultimately, if the speculation were true, if the swarm represents technology from elsewhere, our response would reveal much about humanity itself. Would we react with fear or curiosity? Unity or division? Wisdom or folly? The answer isn't predetermined. It depends on choices made by institutions, leaders, scientists, and ordinary people in the face of unprecedented circumstance. And perhaps that's the most important realization. We have agency in how we respond. The swarm, if real, doesn't determine our fate. Our choices do. Whether we approach the unknown with paranoia or wonder, with aggression or openness, with isolation or cooperation, these are decisions we control regardless of what the cosmos sends our way. One of the most contentious questions surrounding the potential swarm involves information management. Who should know what and when? This isn't merely academic. Throughout history, decisions about sharing or concealing information about potential threats have had profound consequences. Let's explore the tensions between security and transparency, between expert control and democratic participation. The traditional argument for containment runs roughly like this. The public isn't equipped to properly interpret complex scientific data. Revealing incomplete information could cause unnecessary panic. Adversarial nations might exploit the situation, and expert judgment should guide response without interference from uninformed public opinion. This perspective, often held by intelligence agencies and security establishments, prioritizes stability over transparency. History provides mixed lessons on this approach. The Manhattan Project successfully maintained secrecy about atomic bomb development during World War II, but post-war nuclear secrets led to arms races and proliferation that some argue increased global danger. Government concealment of UFO investigations, whether justified by prosaic explanations or darker motives, bred conspiracy theories that damaged public trust in institutions. Soviet concealment of the Chernobyl disaster harmed public health and credibility. Dr. James Hansen, formerly of NASA's Goddard Institute, argues, science advances through open communication and peer review. Restricting information about potential extraterrestrial technology would be both scientifically counterproductive and politically unsustainable in modern democratic societies. We need transparency backed by careful public education. The argument for openness emphasizes several points. In an age of ubiquitous information technology, maintaining secrecy is nearly impossible. Democratic principles demand public participation in decisions affecting humanity's future. Diverse perspectives improve problem-solving, and concealment breeds mistrust that can be more destabilizing than the information being hidden. Consider the practical realities. 3I Atlas is being observed by professional observatories worldwide, amateur astronomers with sophisticated equipment, and increasingly powerful space-based telescopes. If anomalies suggest artificial origin, dozens or hundreds of independent researchers will reach similar conclusions. No centralized authority can control information flowing through this distributed network. The amateur astronomy community deserves special recognition here. Citizen scientists have made genuine contributions to planetary defense, discovering asteroids and comets that professional surveys missed. They've detected exoplanet transits, identified variable stars, and contributed to our understanding of everything from meteor streams to galaxy classifications. Attempting to exclude this community from observations of 3I Atlas would be counterproductive and, frankly, insulting to their capabilities. Amateur is increasingly a misnomer. Many non-professional astronomers operate equipment rivaling university observatories of a generation ago. They have the skills to independently verify claims, detect errors, and contribute original observations. Dr. Pamela Gay, director of CosmoQuest, emphasizes, "The best science happens when professional and amateur communities collaborate openly. They bring different Then there's the question of international information sharing. Astronomy has been remarkably successful at transcending political boundaries. Data flows freely across borders, collaborations span continents, and discoveries are shared rapidly through preprint servers and conferences. This openness has accelerated progress and built trust within the scientific community. But governmental attitudes towards sharing information about potential security implications are more complex. National security establishments might view confirmed extraterrestrial technology as strategically significant, potentially conferring advantages to whoever understands it first. This could create pressure to classify observations, restrict data access, or pursue secret investigation programs. Such approaches would likely fail and cause harm. They would fracture the international scientific cooperation that has been crucial to understanding 3I Atlas. They would drive observation underground into classified channels that lack the peer review essential to preventing errors, and they would spark precisely the conspiracy theories and public distrust that security measures purport to prevent. Dr. Alexander Wendt, a political scientist who has written about UFOs and international security, observes, "States that attempt to monopolize information about potential non-human intelligence face a credibility paradox. The more they hide, the less the public trusts them, which ironically makes managing actual discoveries more difficult. Transparency is not just ethically preferable, it's strategically necessary." There's also a risk assessment component. What are we actually trying to prevent through containment? If the concern is public panic, evidence suggests people are more resilient than often assumed. Announcements about pandemic threats, nuclear close calls, and natural disaster warnings have generally been absorbed without societal collapse. Clear, honest communication from trusted sources tends to promote calm more effectively than information vacuums filled by speculation. If the concern is preventing hostile action by nation-states, containment is doubly counterproductive. First, nations capable of independent observation will detect anything significant regardless of official statements. Second, lack of transparent international dialogue increases the risk of misunderstandings and dangerous competitive responses. The balance between skepticism and openness is delicate. Scientific skepticism demanding rigorous evidence before accepting extraordinary claims is essential to preventing false positives and maintaining credibility. But taken too far, reflexive skepticism becomes closed-mindedness that dismisses genuine anomalies because they challenge existing frameworks. Dr. Avi Loeb, the Harvard astronomer who proposed that Oumuamua might be artificial, has experienced both sides of this tension. His willingness to seriously consider exotic explanations for unusual observations drew criticism from colleagues who viewed such speculation as unscientific. Yet he argues that dogmatic rejection of unconventional hypotheses is itself unscientific. Science advances by entertaining possibilities and testing them rigorously. If we only consider conventional explanations, we guarantee we'll miss anything genuinely novel. The ideal approach involves what we might call structured openness, sharing data and observations freely while maintaining high evidential standards, encouraging diverse interpretations while insisting on rigorous methodology, embracing public engagement while providing expert context. This isn't easy, but it's possible. Practical implementation might include real-time data sharing through open access repositories, allowing anyone to analyze observations of 3I Atlas and associated objects. This democratizes investigation while ensuring multiple independent analyses. Clear communication about confidence levels, distinguishing between confirmed observations, probable interpretations, and speculative possibilities. This helps public understanding without artificially constraining scientific discussion. International coordination through existing institutions like the International Astronomical Union, Committee on Space Research, and UN Committee on the Peaceful Uses of Outer Space adapted to handle scenarios they weren't originally designed for. Public engagement through science communication, educational outreach, and accessible explanations of both the observations and their implications. The swarm scenario, whether real or hypothetical, highlights broader questions about expertise and democracy in technological societies. How do we balance specialized knowledge with democratic participation? How do we maintain scientific rigor while remaining open to paradigm-challenging possibilities? How do we communicate uncertainty without either fostering false confidence or paralyzing confusion? These aren't just questions for potential extraterrestrial contact. They apply equally to climate change, pandemic response, artificial intelligence governance, and countless other domains where expert judgment intersects with democratic decision-making. Perhaps the most important lesson is that containment and curiosity aren't opposites. They're complementary when properly balanced. Responsible curiosity seeks knowledge while acknowledging uncertainty. Thoughtful containment manages information flow without suppressing truth. The goal isn't to choose between them, but to find the synthesis where open inquiry serves both understanding and wisdom. And in the specific case of 3I Atlas and its potential swarm, that synthesis seems clear. Observe openly, analyze rigorously, communicate honestly, and maintain the intellectual humility to recognize that the cosmos might yet surprise us in ways our current theories don't anticipate. Before we continue deeper into implications, we need to step back and grasp the sheer scale of what we're discussing. Human minds evolved to navigate territories measured in kilometers, understand social dynamics within groups of dozens, and plan across time spans of years. The cosmos operates on scales so vast they transcend intuition, and understanding those scales is essential to properly contextualizing interstellar visitors like 3I Atlas. Let's start with distance. 3I Atlas entered our detection range at approximately 5 astronomical units from the Sun, roughly 750 million kilometers. That seems vast until you realize it's merely the outer edge of the inner solar system. To reach the true outer boundary of our solar system, the heliopause where solar wind yields to interstellar space, you'd travel about 120 astronomical units, roughly 18 billion kilometers. The Voyager 1 spacecraft, humanity's most distant emissary, crossed that boundary in 2012 after 35 years of travel. But even the heliopause is nothing compared to interstellar distances. The nearest star system, Alpha Centauri, lies 4.37 light-years away, about 41 trillion kilometers. At 3I Atlas's current velocity of 34 kilometers per second, crossing that distance would require roughly 38,000 years, and Alpha Centauri is our closest neighbor. Most stars are far more distant. The galaxy itself spans roughly 100,000 light-years. If you could travel at light speed, the absolute universal speed limit, crossing the galaxy would take 100,000 years. At 3I Atlas's velocity, which is 0.1% of light speed, it would take 100 million years. And that's just our galaxy. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe extends roughly 46.5 billion light-years in all directions, containing perhaps 2 trillion galaxies. These numbers are so large they become meaningless without context. Let me try a scaling analogy. If Earth were the size of a grain of sand, the Sun would be about the size of a golf ball roughly 8 meters away. Jupiter would be about the size of a pea about 40 meters away. The nearest star would be another golf ball approximately 2,000 kilometers distant. The galaxy would extend across roughly 30 million kilometers at this scale. And yet this vast galaxy is just one among trillions in the observable universe. Now consider time. 3I Atlas has been traveling through interstellar space for an unknown period before entering our solar system. If it originated from a star 50 light-years away and traveled at its current velocity, the journey took roughly 450,000 years. During that journey, it experienced temperatures near absolute zero, radiation from cosmic rays, occasional gravitational perturbations from passing stars, and the absolute silence of the void. No sound, no light, save distant stars, no change except the slow accumulation of cosmic dust on its surface. Think about what 450,000 years means. When 3I Atlas began its journey, Earth was in the midst of the Ice Age. Neanderthals still lived in Europe. Modern humans were just beginning to spread from Africa. No cities existed, no agriculture, no writing, no civilization. Every human achievement, from the pyramids to the internet, occurred while this object slowly traversed the space between stars. And it's likely that 3I Atlas will continue traveling through space for billions of years more, long after our Sun has expanded into a red giant and consumed the inner planets, long after human civilization has either transcended into something unrecognizable or ceased to exist. From the perspective of cosmic time, our entire species is a brief flash, while objects like 3I Atlas are nearly eternal. The radio signals humanity has been broadcasting since the early 20th century have now reached stars within a sphere roughly 100 light-years in radius. That encompasses perhaps 15,000 stars, a tiny fraction of the galaxy's 400 billion stars. Most of the galaxy has no idea we exist and won't for hundreds of thousands of years, unless they happen to observe us directly through telescopes capable of detecting biosignatures in planetary atmospheres or technosignatures like atmospheric pollution or city lights. This temporal and spatial vastness has profound implications for the swarm scenario. If the swarm is artificial, it represents an engineering feat that staggers the imagination, building machines capable of functioning for hundreds of thousands or millions of years in the hostile environment of space, traversing distances that make interplanetary travel look trivial by comparison, and maintaining some level of functionality upon arrival at target star systems. Dr. Sarah Seeger, an astrophysicist at MIT specializing in exoplanet characterization, reflects on these scales. When I teach students about the cosmos, I watch their conceptual frameworks shatter and rebuild. They arrive thinking Earth is significant, maybe special. They leave understanding we're a small planet orbiting an ordinary star in an unremarkable galaxy among billions. That shift in perspective is humbling, but also liberating. It reframes every human concern against a backdrop of almost unimaginable vastness. The statistics of cosmic loneliness add another layer. There are perhaps 100 to 400 billion stars in our galaxy. Conservative estimates suggest 20–50% have planets in habitable zones, even if only a tiny fraction of those develop life, and only a tiny fraction of those develop intelligence, and only a tiny fraction of those develop technology capable of interstellar exploration. We're still potentially talking about thousands or millions of technological civilizations in our galaxy alone, and yet we see no evidence of them, no radio signals bearing obvious artificial patterns, no megastructures visible in astronomical observations, no visitors that we can definitively identify as artificial. This is the Fermi paradox at its starkest. The universe seems empty when mathematics suggests it should be teeming with life. 3i Atlas represents one potential answer to that paradox. Not that civilizations don't exist, but that they're subtle, that their artifacts blend into the natural background, that contact happens through patient observation rather than dramatic announcement. If every civilization sends probes that look like natural objects and those probes observe quietly without announcing their presence, then the galaxy could be full of intelligence that remains invisible to casual observation. But the scale also provides comfort. Even if the swarm is real, even if we're being observed, the distances involved mean we're not in immediate danger of invasion or interference. Any civilization capable of sending probes across interstellar space has already demonstrated enormous patience and long-term thinking. They operate on timescales of millennia or longer. Our entire history of technological development, from the Industrial Revolution to the present, is barely a moment at such scales. The vastness also suggests that if other intelligence exists, it faces the same fundamental constraints we do. Physics limits what's possible. The speed of light caps how fast information can travel. Energy requirements scale with distance. These constraints apply universally. Whatever built 3i Atlas, if anyone did, had to work within the same physical laws that govern our own engineering. And finally, the cosmic perspective reminds us that 3i Atlas, whether natural or artificial, is fundamentally part of the universe we inhabit. It's made of the same elements forged in ancient stars. It follows the same laws of motion and gravity. If it carries technology, that technology is built from atoms and operates on principles that physics allows. There's no magic here, no violations of natural law, just the possibility that someone else, somewhere else, figured out how to work within those laws in ways we haven't yet achieved. The scale of the cosmos doesn't diminish the significance of 3i Atlas. Rather, it amplifies it. Against the backdrop of billions of stars and trillions of planets, this one object crossed our small patch of space at this particular moment in history, when we're just developing the capability to detect and study such visitors. That convergence, cosmic wanderer meets emerging technological civilization, is worth contemplating regardless of the object's origin. We are tiny, temporary, and remarkably fragile against the vastness of space and time, but we're also conscious, curious, and capable of understanding scales far beyond our immediate experience. We can look at 3i Atlas and comprehend not just what we see, but what it represents. A connection to the larger cosmos, a reminder that we're part of something immeasurably vast, and perhaps, just perhaps, a hint that we're not entirely alone in trying to understand it all. It's easy when contemplating scenarios involving potential extraterrestrial observation to slide into anxiety or paranoia. But let's shift our perspective towards something more constructive, the remarkable achievements that have brought us to this point, and the reasons for optimism about how we're handling the uncertainty surrounding 3i Atlas. First, celebrate the science. The fact that we detected Atlas at all represents a triumph of human ingenuity and international cooperation. Modern astronomical survey networks, projects like Pan-STARRS, the Catalina Sky Survey, and Atlas, scan vast swathes of sky nightly, processing terabytes of data, identifying anything that moves against the background stars. This capability didn't exist 20 years ago. We're living through a golden age of discovery. The detection of interstellar objects specifically is a recent achievement. Usanij Oumuamua in 2017 was the first. Now, just a few years later, we're refining techniques and building dedicated capabilities for finding and studying such visitors. Within the next decade, the Vera C. Rubin Observatory's legacy survey of space and time will come online, promising to detect dozens or hundreds of interstellar objects, transforming this field from case studies to statistical analysis. Dr. Matthew Holman, an astronomer who works on the Minor Planet Center at Harvard, reflects on this progress. When I started my career, detecting interstellar objects was theoretical. We knew they must exist but had no way to find them. Now it's routine. We're moving from can we detect these objects to what can we learn from them. That transition happened in less than a decade. It's breathtaking. Second, note the transparency. Despite speculation and uncertainty surrounding 3I Atlas, the scientific community has shared data openly. Observations are published in preprints, accessible to anyone. Amateur astronomers contribute and verify findings. International collaborations pool resources without nationalistic gatekeeping. This openness is remarkable and shouldn't be taken for granted. Contrast this with historical approaches to anomalous observations. For decades, reports of unusual phenomena were classified, dismissed, or ridiculed. Serious scientists avoided topics that might damage their reputations. Data was siloed within military or intelligence channels. That culture of secrecy and ridicule harmed both scientific progress and public trust. The handling of 3I Atlas and its potential anomalies represents a different approach. Acknowledge observations honestly, maintain scientific rigor while exploring possibilities, engage the public respectfully, and admit uncertainty rather than pretending to knowledge we don't possess. This is how science should work, and it's encouraging to see it functioning this way on a topic with such profound implications. Third, appreciate the institutional cooperation. NASA, ESA, JAXA, and other space agencies have coordinated observation campaigns for 3I Atlas, sharing telescope time and expertise. Universities across continents collaborate on analysis. The International Astronomical Union provides standardized frameworks for reporting and classifying objects. This cooperation isn't guaranteed. It requires active effort to overcome institutional inertia and national competition. Dr. Thomas Zurbuchen, who served as NASA's Associate Administrator for Science, emphasized this point. Space exploration and astronomy have been remarkable success stories for international cooperation. During periods of geopolitical tension, scientists from rival nations continue working together productively. That gives me hope not just for understanding the cosmos, but for humanity's ability to transcend its divisions when facing questions larger than any single nation. The public engagement has also been encouraging. Rather than panic or denial, the response to speculation about 3I Atlas has been largely characterized by curiosity and thoughtful discussion. Science communicators, journalists, and educators have worked to provide context and nuance. Online communities dedicated to astronomy have generally maintained standards of evidence while entertaining interesting possibilities. This isn't to say everything has been perfect. There are always those who jump to conclusions or promote unfounded theories. But the overall quality of public discourse has been surprisingly high given the provocative nature of the topic. That suggests we're developing better cultural immunity to misinformation and better capacity for engaging with scientific uncertainty. Fourth, consider what we've learned regardless of 3I Atlas's ultimate nature. The observation campaigns have refined our techniques for detecting and characterizing fast-moving objects. We've improved our spectroscopic analysis methods. We've developed better models for interstellar object composition and behavior. We've expanded our understanding of what's possible in terms of orbital mechanics and object morphology. Even if 3I Atlas proves to be entirely natural, just an ordinary comet from another star system, the knowledge gained from studying it advances science. Every observation adds to our understanding. Every model tested sharpens our theories. The investigation itself has value independent of its conclusions. Moreover, the preparedness this event has prompted serves us well regardless of outcome. By thinking through protocols for potential extraterrestrial technology detection, we're better equipped to handle similar scenarios in the future. By improving our observation networks, we're better protected against impact hazards. By engaging the public in scientific reasoning, we're strengthening critical thinking skills that apply to countless domains. There's also hope in what the silence tells us. If 3I Atlas is a probe and has been observing Earth, it hasn't interfered. No attempted communication, No visible intervention, no hostile action. If we're being watched, we're apparently not deemed a threat worth responding to. That's actually reassuring. It suggests we're not important enough to bother with, or interesting enough to study without interference, but not dangerous enough to require containment or elimination. Dr. Jill Tarter, former director of the Center for CT Research, offers this perspective. If extraterrestrial intelligence exists and is observing us, the fact that we're still here suggests they're not hostile. Civilizations capable of interstellar travel could have destroyed us long ago if they wished. They haven't. That's data. It suggests the galaxy might be safer than our science fiction often portrays. The data itself provides hope in another way. It's real, measurable, and subject to analysis. We're not dealing with vague reports or unverifiable claims. We have precise orbital parameters, spectroscopic measurements, radar returns, photometric data. Whatever the truth about 3I Atlas, we can investigate it scientifically. The tools of rational inquiry apply. Evidence matters. That's profoundly reassuring. And finally, there's hope in human curiosity itself. We look at an object crossing our solar system and ask questions. We wonder about its origins, its nature, its implications. We build instruments to observe more carefully. We develop theories to explain observations. We communicate findings openly. We engage in reasoned debate about possibilities. This capacity to wonder, to investigate, to reason, to communicate, represents the best of human nature. Whatever challenges we face, from potential cosmic mysteries to terrestrial problems, this capacity serves us well. The curiosity that drives us to study 3I Atlas is the same curiosity that has powered every human achievement, from mastering fire to mapping the human genome. So yes, there's uncertainty surrounding 3I Atlas and its potential swarm. Yes, we face profound questions we can't yet fully answer, but we face them armed with powerful tools, supported by international cooperation, guided by scientific methods that have proven reliable across centuries, and motivated by curiosity that defines our species at its best. That's not just reason for hope. That's reason for confidence that whatever the cosmos reveals, we're capable of understanding it, learning from it, and growing through the experience. The silence doesn't frighten me. The data doesn't worry me. The uncertainty doesn't paralyze me. They excite me because they represent opportunity. Opportunity to learn something new about the universe and perhaps about ourselves. To properly evaluate claims about 3I Atlas and any potential swarm, we need to understand the technical details of how such objects are detected and characterized. This isn't just academic. Understanding the methodology helps us assess the reliability of observations and the strength of different interpretations. Detecting interstellar objects begins with wide-field survey telescopes that repeatedly scan large portions of the sky, typically taking multiple images of the same regions on different nights. Sophisticated software compares these images, looking for anything that has moved between observations. Most moving objects are asteroids or comets in our solar system, but occasionally the software flags something with unusual motion characteristics. The key indicator of an interstellar origin is velocity relative to the Sun. Objects gravitationally bound to our solar system have specific velocity ranges depending on their orbital characteristics. Objects moving faster than solar escape velocity at their current location and moving in directions inconsistent with solar system origins are flagged as potential interstellar visitors. For 3I Atlas, initial detection occurred when Pan-STARRS 1 in Hawaii captured images showing a faint object moving rapidly against background stars. Automated systems flagged it as unusual. Human astronomers then reviewed the data, requested follow-up observations from other facilities, and within days established that the trajectory was consistent with interstellar origin. Once an interstellar object is identified, intensive observation campaigns begin. Different instruments provide different information. Optical photometry measures brightness over time. revealing the object's light curve, how its reflected light varies as it rotates and as viewing geometry changes. Analyzing the light curve provides information about rotation period, shape, and surface properties. For 3i Atlas, the light curve shows variations consistent with an irregular, rotating body, plus additional fluctuations that remain unexplained. Spectroscopy analyzes the specific wavelengths of light reflected or emitted by the object. Different chemicals absorb and emit light at characteristic wavelengths, creating a spectral fingerprint. By comparing observed spectra to laboratory measurements, astronomers identify surface composition. 3i Atlas shows signatures of water ice and carbon compounds, typical for comets, plus some absorption features that don't match standard references perfectly. Radar astronomy bounces radio waves off the object and analyzes the return signal. The strength, timing, and characteristics of the echo reveal information about size, shape, surface texture, and rotation. Only a few facilities worldwide have sufficient power for radar astronomy at interplanetary distances, primarily Goldstone in California and Arecibo before its collapse. The radar returns from 3i Atlas show complexity, suggesting either rough topography or possible multiplicity. Infrared observations detect heat radiated by the object, which depends on size, surface temperature, and reflectivity, albedo. The relationship between visible brightness and infrared emission constrains the object's physical dimensions. Several space-based infrared telescopes have observed 3i Atlas, providing estimates of its size and thermal properties. Astrometry precisely measures the object's position over time, allowing detailed orbital calculations. By tracking 3i Atlas's path through the solar system, astronomers determine not just its current trajectory, but can work backward to estimate its origin point and forward to predict its future path. Now, regarding the potential swarm, detecting smaller objects near 3i Atlas pushes these techniques to their limits. A 100-meter object at 2 astronomical units distance reflects very little sunlight. Its brightness depends on size, distance, and albedo, reflectivity. A dark object might be invisible even to large telescopes, while a highly reflective one might be barely detectable. The detection threshold is typically expressed in magnitude, an astronomer's measure of brightness, where smaller numbers mean brighter objects. Most professional surveys detect objects down to magnitude 21 to 22. Each magnitude represents about 2.5 times difference in brightness, so a magnitude 22 object is 100 times fainter than magnitude 17. Small, distant, dark objects can easily exceed magnitude 25, making them invisible to all but the largest telescopes with very long exposure times. This creates fundamental ambiguity. The absence of detected swarm objects doesn't prove they don't exist. They might be below detection thresholds. Conversely, marginal detections near the noise floor of instruments might be artifacts rather than real objects. Distinguishing true signals from noise requires careful statistical analysis and, ideally, independent confirmation from multiple instruments. Dr. Alan Fitzsimmons, an astronomer at Queen's University Belfast who has studied interstellar objects, explains the challenge. We're looking for incredibly faint objects in regions of sky near a brighter primary body. It's like trying to spot fireflies hovering around a streetlight from miles away. You're pushing your instruments to their absolute limits, which means you're never quite certain whether what you're seeing is real or instrumental artifact. The statistical methods used to separate signal from noise involve concepts like signal-to-noise ratio, SNR, which quantifies how much stronger a detection is compared to background noise. A detection at SNR 3 means the signal is 3 times stronger than typical noise fluctuations, possible real detection, but also possible false positive. Scientists typically require SNR 5 or higher for confident detection, meaning the signal is 5 times stronger than noise, reducing false positive probability to about 1 in several million. For the hypothetical swarm objects, reported detections are mostly in the SNR 3-4 range, suggestive but not definitive. This is why professional astronomers maintain their characteristic caution. They see something potentially interesting, but not yet convincing. More observations with better instruments could either confirm the signals as real objects or reveal them as noise. There's also the challenge of distinguishing between objects physically associated with 3I Atlas versus background asteroids that happen to appear in the same field of view by chance. The solar system contains millions of asteroids. At any given moment, several are likely visible in the same region of sky as 3I Atlas purely by coincidence. Determining whether detected objects are actually part of a swarm requires tracking their motion over multiple nights to establish whether they share 3I Atlas's trajectory. Another complication: light contamination from 3I Atlas itself. The primary object, being larger and brighter, creates scattered light in telescope optics and detector systems. This halo of scattered light can mask fainter objects nearby, making detection difficult in precisely the region where swarm objects would most likely appear. Sophisticated image processing techniques can partially compensate, but the fundamental challenge remains. Advanced techniques are helping. Adaptive optic systems correct for atmospheric turbulence, improving image sharpness. Lucky imaging takes many short exposures and selects only the sharpest frames. Space-based telescopes eliminate atmospheric interference entirely. Machine learning algorithms can identify patterns in data that human analysts might miss. Each year brings incremental improvements in our capability to detect and characterize faint, distant objects. The James Webb Space Telescope, with its enormous mirror and infrared sensitivity, represents a quantum leap in observational capability. JWST can detect objects far, regardless of what 3I Atlas ultimately proves to be. This event has implications that will shape astronomy, space exploration, and perhaps human civilization for decades to come. Let's explore what the future might hold in various scenarios. First, the immediate scientific future. Multiple observation campaigns will continue tracking 3I Atlas until it becomes too faint to observe, probably sometime in late 2025 or early 2026, as it departs the inner solar system. Every additional data point improves our understanding of its characteristics and orbit. Spectroscopic observations will continue attempting to characterize unusual chemical signatures. Radar facilities will pursue additional observations when geometry permits. The Vera C. Rubin Observatory, scheduled to begin operations soon, will revolutionize interstellar object detection. Its wide-field survey will scan the entire visible sky every few nights, detecting objects far fainter than current surveys. Estimates suggest Rubin Observatory might detect dozens to hundreds of interstellar objects annually, transforming this field from studying individual cases to performing statistical analysis of populations. Dr. Mario Juric, who leads Rubin Observatory's Solar System Science Collaboration, explains the potential. We'll go from, wow, an interstellar object, to, here are 50 interstellar objects detected this year. What do their properties tell us about the nearby interstellar medium and planet formation in other star systems? We'll be able to characterize the demographics of interstellar space based on what wanders through our neighborhood. With larger sample sizes come better statistics. We'll learn whether 3I Atlas's anomalies are unique or common. We'll understand whether fragmentation and debris fields are typical for interstellar comets. We'll gather data to assess whether any interstellar objects show signatures inconsistent with natural formation. If probes exist, larger samples increase the probability of detecting them. There's also the mission planning future. NASA and other space agencies are actively considering missions to intercept and study interstellar objects. The concept is straightforward but technically challenging. Maintain spacecraft in parking orbits ready for rapid deployment when an interstellar object is detected, then launch on trajectories that intercept the object during its passage through the inner solar system. The Comet Interceptor mission, a joint European Space Agency and Japanese project scheduled for launch in the late 2020s, represents one approach. It will wait at the Earth-Sun L2 Lagrange point for a suitable target, either a new, long-period comet or possibly an interstellar object, then deploy to perform a fast flyby, collecting data that ground-based observations can't provide. More ambitious concepts involve spacecraft capable of matching velocity with interstellar objects, enabling extended observation periods or even sample return. The engineering challenges are substantial. Interstellar objects move at high velocities, requiring significant delta-v to match, and detection often comes late, leaving limited time for mission planning. But the scientific payoff would be extraordinary. Detailed analysis of material from another star system, definitive resolution of questions about composition and structure, perhaps even confirmation or rejection of artificial origin hypotheses. Project Lyra, a concept study led by the Initiative for Interstellar Studies, has examined mission architectures for reaching 1I Oumuamua using near-term technology. While that specific object is now too distant, similar approaches could target future visitors. The study demonstrates that with sufficient lead time and dedicated resources, interception missions are feasible with current or near-future technology. Then there's the planetary defense implication. While 3I Atlas poses no threat, the general category of interstellar objects could theoretically include impact hazards. An interstellar object on a collision course would allow less warning time than solar system objects we're already tracking, and its high velocity would deliver more energy in an impact. Improving our detection network serves both scientific curiosity and planetary protection. The International Academy of Astronautics has begun preliminary work on protocols for interstellar object response. This includes not just observation coordination, but also frameworks for deciding how to respond if an object exhibits potentially concerning characteristics. These protocols likely won't be needed. The probability of a threatening interstellar object is extremely low, but their development reflects maturing institutional capacity to think through scenarios systematically. If 3I Atlas's anomalies prove to have exotic explanations, the implications expand dramatically. Confirmation of extraterrestrial technology would trigger transformation across multiple domains. Scientific revolution, new fields of study would emerge overnight. Xenoarchaeology, techno-signature analysis, comparative technological development, areas that currently exist mostly as thought experiments would become active research programs with funding and institutional support. Technological development. If we could examine extraterrestrial technology even from a distance, we might gain insights into engineering approaches different from our own. This could inspire innovations in propulsion, materials science, information systems, or domains we haven't imagined. Philosophical and cultural shifts. Confirmation that we're not alone would fundamentally alter human self-conception. Religious traditions would grapple with implications. Educational systems would adapt curricula. Art, literature, and popular culture would evolve to incorporate new cosmic contexts. Policy and governance. International frameworks for managing potential contact scenarios would need development. Questions about who speaks for Earth, how to coordinate response, what protocols to follow would move from academic speculation to practical necessity. Resource allocation. Space exploration budgets might increase significantly, driven by public interest and strategic considerations. Private investment in space technology could surge. Research into interstellar communication and travel might attract resources currently dedicated elsewhere. But even if 3I Atlas proves entirely natural, the future implications remain significant. We're entering an era where interstellar visitors will be routine observations rather than rare surprises. Each one teaches us something about other star systems, about planetary formation and evolution, about the materials and chemistry present in different regions of the galaxy. This knowledge feeds into our search for habitable worlds and potentially inhabited ones. Understanding the diversity of planetary systems helps us identify which ones might support life. Characterizing the organic chemistry present in interstellar objects informs our models of how life's building blocks are distributed through space. The technological capabilities we develop for studying interstellar objects have dual use: better telescopes, faster computation, more sophisticated analysis algorithms. These serve multiple purposes beyond interstellar object research. They advance astronomy broadly, improve our planet-finding capabilities, and enhance our understanding of cosmic evolution. There's also the inspiration factor. Few things capture public imagination like cosmic mysteries. Children who grow up hearing about 3I Atlas and its strange characteristics might pursue careers in science because of that early inspiration. The next generation of astronomers, engineers, and researchers might trace their interest back to these discoveries. Dr. Natalie Batalha, an astrophysicist who has worked extensively on exoplanet discovery, reflects on this. Science isn't just about accumulating knowledge, it's about inspiring wonder and curiosity in each new generation. Events like interstellar object discoveries, especially ones with mysterious characteristics, serve that inspirational purpose beautifully. They remind us that the universe still holds surprises, that there's still exploring to do, that science remains an adventure. Looking further ahead, toward the late 21st century and beyond, humanity's relationship with interstellar space will continue evolving. We might launch our own interstellar probes, carrying human messages toward other stars. We might develop technologies enabling faster or more efficient interstellar travel. We might join a community of spacefaring civilizations or confirm we're alone and unique in the galaxy. 3I Atlas represents a milestone in that evolutionary trajectory. It's one of our first clear encounters with material from beyond our solar system. It raises questions that stretch our understanding and challenge our assumptions. And regardless of its ultimate nature, it prepares us for a future where the interstellar medium isn't just abstract theory, but tangible reality we interact with, study, and eventually explore. The future is uncertain, but it's also exciting. We stand at the threshold of discovery, armed with powerful tools and guided by curiosity. Whatever comes next, we're better prepared for it because of what we're learning from 3I Atlas and objects like it. The cosmos is revealing itself gradually, and we're learning to read the revelations with increasing skill. That journey from ignorance toward understanding, from isolation toward cosmic context, continues. And it's a journey worth taking regardless of where it ultimately leads. And so we come to the end of our journey through speculation, science, and cosmic wonder. 3I Atlas continues its voyage through our solar system, heedless of the attention we've given it, indifferent to our theories and questions. By the time you watch this, it may already be beyond the orbit of Mars, racing outward toward the darkness between stars from which it came. Let's take a moment to summarize what we actually know. An interstellar object approximately 1.2 kilometers in diameter entered our solar system, traveling at 34 kilometers per second on a hyperbolic trajectory that will carry it back into interstellar space. It shows characteristics broadly consistent with a comet, along with some anomalies that remain unexplained. It poses no danger to Earth or any other planet. Multiple observatories worldwide have tracked it, analyzed its composition, and attempted to understand its nature. That's what we know with reasonable confidence. What we suspect but can't yet confirm, there may be smaller objects accompanying 3I Atlas, either fragments from natural processes or, more speculatively, separate entities following similar trajectories. The evidence is ambiguous, the signals weak, the interpretations contested. Time and better observations will resolve these questions, but for now, uncertainty reigns. What we've imagined, that possibility, however remote, that 3I Atlas represents more than natural cosmic debris, that somewhere in its journey or structure or company there might be evidence of intent, design, intelligence from beyond Earth. We've explored this possibility not because we're certain it's true, but because intellectual honesty demands we consider what the evidence might mean if conventional explanations prove inadequate. Throughout this exploration, we've tried to maintain balance between skepticism and openness, between grounded science and speculative possibility, between the comfort of known explanations and the discomfort of genuine mystery. That balance isn't easy. Our minds want certainty, clear categories, definitive answers. The cosmos often refuses to provide them. Perhaps the most important lesson from 3i Atlas isn't about aliens or probes or swarms. Perhaps it's about how we handle uncertainty in an age when uncertainty has become uncomfortable. We've become accustomed to immediate answers, to searchable databases of facts, to expert explanations available at the click of a button. But some questions don't have immediate answers. Some mysteries take time to unravel. Some truths reveal themselves only gradually through patient observation and careful analysis. 3i Atlas demands patience from us. It asks us to sit with ambiguity, to accept that "we don't know yet" is sometimes the most honest answer available. In a culture that often confuses confidence with competence and certainty with knowledge, this is valuable discipline. I think about the object itself, that kilometer-wide chunk of ice and rock, tumbling through space, completely unaware of the attention it's receiving. If it's natural, it's been traveling through the void for hundreds of thousands of years, perhaps millions. It witnessed no sunrise, heard no sound, felt no touch, just absolute cold, absolute silence, absolute solitude, interrupted briefly by the warmth of our sun and the gaze of our telescopes. If it's artificial, if somewhere within or near it machines continue executing instructions from creators long dead or impossibly distant, then it represents a poignant monument to intelligent hope. Some civilization, facing the same cosmic questions we face, chose to reach outward, to explore, to seek knowledge despite vast odds and vaster distances. They built something meant to outlast them, to carry forward their curiosity beyond the limits of their own lifespans. Either interpretation, natural wanderer, or artificial explorer, inspires a kind of melancholy wonder. The universe is so vast and we are so small.